Okay, everyone, let's get started. So we have another quiz that's posted on Blackboard. So just go on there and take it by Friday. It only has 6 questions on it. It just covers the material that I'm going to go over today. Okay, we had quiz 1 last week. I go over that really quickly. This first question asks, it's about the RISC-V assembly, and it asks if you're translating the C4 loop on the left, what instruction is missing in the corresponding assembly code on the right. So that first instruction basically loads the address of A into a register because A is an array and C arrays are pointers. So the load address is dereferencing, no, it's referencing A. It's putting the address of A into X1. And then we initialize register X10 with 40, and it should be 10, but we're basically multiplying the loop iterator by 4 because we're accessing 32-bit words in the array. Okay, so that you can see there's this 4 multiplier in there, and then same thing here with initializing I, which in this case is x2 with 8 instead of 2. We've multiplied that by 4, and then we start the loop, and you can see that we are decrementing x3 by 4, and yes, we're doing that because the I minus 1. Then we're dereferencing the A array to load the value at A I minus 1. And then we actually do the load. So the X4 is the address that we're calculating for that. And we load that element into X5. And then we decrement X4 again by -4. So we go back one more word in the address. And then we load, in this case, X6 with A I minus 2. And then we add the 2 elements together, and then we increment I by 4. And then we go back to the beginning of the loop. So the only thing this is missing is the pretest condition for the loop. So the loop, so we initialize, you can see that we initialize I before the loop begins, and we increment I as the very last instruction of the loop body, but we don't have a pretest. The pretest is supposed to be I less than 10, but you'll notice that the test that we have in here is the opposite. It's the opposite of I less than. It's greater than or equal. We check to see if I, which is x2, is greater than or equal to x10, which was our limit of 40. And if that is true, then we exit the loop. So remember that this is one of the things on my list of annoyances of assembly language programming is whenever you have an if statement, or in this case a loop, you're going to want to reverse the logic of the branch condition, because if it's false, you fall through, which in this case, we want to continue with the loop. So we want to fall into the loop body if the condition is false, by which we mean the continuance condition is not true, right? You guys with me? Does it make sense? I don't know if I explained that very well. But we had to reverse the logic of that. So if you look in the C code, it's I less than 10, whereas in the assembly language, it's checking to see if I is greater than or equal to 10. Because if it is, then we take that as a chance to go to exit. So we break out of the loop. Okay. All right. What does the following code perform? So in this case, we're taking whatever's in X3, shifting it 16 bits to the left, which puts zeros into the 16 bits on the right, and then we shift X3 to the right, which puts 16 zeros into the 16-bit positions on the left. So we're taking the lower half of X3 and moving it to the upper half, and we're taking the upper half and moving it to the lower half, and then there's this OR. We store the results of those in 2 different registers, X2 and X3, and then we OR together those to form a final result. So basically what that does is it swaps the upper half and lower half of X3, whatever was in X3. Okay, two operations you can perform on SystemVerilog code is simulation and synthesis. What's the problem with the SystemVerilog module below? Well, you can see that if this were normal sequential semantics, that would be fine. You can, most programming languages have no issue with you reassigning a variable on different lines of code. But in this case, since this is concurrent semantics and each one of these assign statements creates a circuit, a logic circuit, then we can't reassign Z because that would essentially mean that it was double driven. Now, one of the things that's interesting about this, I didn't realize this, actually. I don't know when this changed. I think I lost track of this. But if you were to put this in and try to run it, so if I open up a terminal here and I say, if I edit, what did I call that? myfunc.csv. Yeah, so I already have it in here. Actually, I don't have it. This is different. Never mind. Delete all that. And insert. Okay, so this is the same code from the slide. I just pasted it in here. Okay, and then we vlog. Okay, so it wouldn't even compile with vlog because it says that Z is driven by more than one continuous assignment. So I couldn't even compile that. Shit. I thought there were cases in the past, maybe it was just with Verilog where it would compile, but then you would get an X on Z. But this won't even compile in this case. Okay, so that's the issue there. Does SystemVerilog support structural, behavioral, both? How many possible values can be assigned to type logic is 4. And then, in this case, consider the following SystemVerilog modules, bottom and top. What's the value of A and Y within my thing? So this is just demonstrating how signals get renamed at different points in the hierarchy. So we have A and Y in the top module and in the bottom module, and they are swapped because A is assigned to Y and Y is assigned to A. Okay. Now you can also simulate this too, by the way. If you take this, I copy that, and I go back up here, I can just put that in there and save it. And notice that the file I saved in is still called myfunc.sv. Now normally you would save these in two different files where the file names would match the names of the modules, but that's just a convention. I can actually compile this and just call it, leave it as myfunc.sv. And then if I open up the simulator with vsim, if you go into the work, this work library is where they're at. So you can see that myfunc is still in there because it's the compiled version of it. And of course I've got bottom and top. So if I right click on top and say simulate, you can see Y and A here. Okay, so you can see the design hierarchy over here. It's kind of small, but you got top in my thing. So I can take top and I can drag it into the wave here, and I could take my thing and drag it into the wave. And yeah, sorry, my thing. Okay, so you can see, I know it's kind of small. Hold on a second. Let me see if I can magnify this. Yeah, here we go. Oh, too much. Oh, okay. So yeah, so you can see when I drag those in, you've got Y and A there, but you can see even in the way they're labeled, it's top Y, top A, top my thing A, top my thing Y, right? And then you can, now the problem is we're not assigning them yet, right? Are we assigning them in here? Yeah, we assign Y. Yeah, we got an assign for Y. Yeah, so I think we can just run that. We don't have to do anything to it. Yeah, there you go. So then if I put the cursor there, you can see, zoom in again here. Yeah, you can see that they're just swapped. So Y and A is 0 and 1. And down at the bottom it's, sorry, y is 1, y and a are 1 and 0, and then it's 0 and 1. They're in a different order, though. Sorry. So, it should be, there you go. That looks better, right? So the y is on the top and the bottom's on the a. Or a is on the bottom. Okay, so yeah, that just swaps the values. Okay. Assume the following SystemVerilog code snippet. What's the value of A? Okay, this is another one that is a little weird. So what you would expect to happen here is if I assign A to be a high impedance, it means nothing's driving, that statement isn't actually driving A to a value. And the second line says assign it to 0. You would expect the 0 to overpower the Z, right? It should replace the Z. But what actually happens is, again, I'm going to go up here and I'm going to put that, no, didn't work. Okay. Okay. All right. And then I need a module for this, so I'm just going to say module foo, and then end module, and then this is logic A. Okay. So there you go. And then we will go back to model sim here and restart. That'll, oh, I got to recompile first. Vlog myfunc. Okay, so you can see here we're still getting that same error. A is driven by more than one continuous assignment. That's weird, right? I thought the whole point of the Z was so you could do that. So I forgot about this, but to fix that, you can actually, it's a kind of an obscure difference between the logic type and the wire type. So I should have declared it as a wire, and we don't really, foreground, here we go. Sorry, let me get this organized here. Okay, yeah, so I just changed the declaration to wire, and so if we vlog myfunc, okay, so then it compiles, and if you run it, it will, let's see, restart it and run. Oh, sorry, I got to change. Sorry, I got to change to, let me do a refresh here, or update. There we go. We want foo, actually. So let's simulate foo. Because I was still on myfunc. All right, and then we have A here, and then we run that, and there you go. See, it's 0, right? So we don't, typically in this class, we don't use the wire type just to simplify things. We use logic for all the binary signals. But there are some slight differences between wire and logic, but we generally just stick to logic. How many bits comprise the signal A in the SystemVerilog snippet below? It's going to be it's 3 down to 0. It's inclusive, so it's 4 bits. And to what value is A set in the SystemVerilog snippet below? So this one is a little strange because this one is a ternary, and ternary has the lowest priority. So it's going to evaluate the condition first, even though I don't have any parentheses in there. And then, according to the order of operations, it's going to do the shift left before it does the comparison. So what ends up happening is you have a 2-bit signal shifted left by 1 bit. That's going to give you, it's going to be like multiplying it by 2, right? So it's going to give you 4. Except the weird thing is that you don't really know how many bits the result is going to be in. Like, so for example, if this shift operation constrains the output to the same number of bits as the argument, as the operand, then what will happen is if you take 2 in 2 bits and shift it to the left by 1 bit, it's going to be 0, right? Because you'll have shifted one of your 1 bits off, your most significant 1 bit. On the other hand, if Verilog does this shifts and uses 3 bits to represent the results, meaning that 2 shifted by 1 bit to the left is 4, but now in 3 bits instead of 2 bits, then this comparison will be true, in which case the whole statement will evaluate to be 1, right? Well, as it turns out, if you run it, it'll actually evaluate this sub-expression as being 3 bits, right? So that ends up being 1. So yeah, so the first thing that happens is the shift, which gives you, it shifts the value of 2 to give you 4, and effectively increases the number of bits from 2 to 3. The comparison ends up being true, and so the evaluates to 1. Okay, so in the SystemVerilog code below, to what value is signal A set? This one is where, this is what I would say is one of the most confusing things about reading Verilog code, because as I mentioned, this my thing, when you look at the top level module, you don't know which of A, you've got ports A and Y, you don't know which one's an input and which one's an output, right? So you have to go back and look at my thing, and you can see that Y is an output. So if you come back to top, you can see that Y is connected to A, which means my thing is going to be driving A, but look, there's already something else driving A, this assignment statement, so you're going to end up, that'll end up being in conflict. And I already tried, if you put this into QuestaSim, it'll give you another error saying that you can't double drive that signal. So this actually won't even compile because of that. QuestaSim recognizes the conflict. Okay, so that's it. Any questions? Okay, so like I said, we have another quiz. It's similar but shorter, and due on Friday. Okay, so last time we talked, I talked about structural HDL, which is where you instance modules inside of other modules. Port maps, which is connecting inputs and outputs of modules that you instantiate. That creates a hierarchy. And as you go across that hierarchy, the same signal could have the same name or have different names across different levels of the hierarchy, which is we saw in that quiz question when I swapped A and Y, right, in top and bottom. So A and Y in top and bottom were the same signals, but their names were switched depending on whether you were looking at them in top or in bottom. And then we talked a little bit about behavioral HDL. Basically, the only thing we covered there was the continual. Yikes, sorry. I should say continuous. Continuous assignment statement. Continuous assignment statement, that's the statement that starts with a sign. So it's for making basic logic multipliers, little snippets of Boolean algebra, that kind of stuff. And it creates every continuous assignment statement creates what is essentially a logic circuit. In VHDL, they call them concurrent assignment statements. In Verilog, they're continuous assignment statements, but they're in both languages, just with different names. We also mentioned I briefly mentioned this, but the ternary operator, when combined with an assign statement, can be used to create lookup tables, pretty much. And this was actually how I was expecting all of you guys to do the 7-segment decoder in Lab 2, but I think at least the ones that I visited in lab, a lot of you guys figured out how to use an assign statement and use an if statement or a case statement, which I'm going to talk about today. I didn't get that far yet. In fact, I'm a little bit behind relative to the labs. I'm hoping to catch up today. But yeah, you could create the 7-segment decoder with just a ternary statement, nested ternary statement. This creates kind of like a if-then-else sort of, where you have the condition and then what you want that to be if the condition is true. So for example, if the 4-bit input were 0, then you could have it spit out whatever the 7 segments are for 0, and then a colon, and then on the next line you could put another condition, right? And then at the end you have to have kind of the else case, right? The catch-all, the default case, right? We also talked about numeric constants, where you specify a bit width, apostrophe, a base, and a value. Don't get trapped, though, by this. You'll notice that Microsoft PowerPoint change this apostrophe to like a smart apostrophe. So this actually wouldn't work. It should be a regular apostrophe, the way I have it here. Then we also talked about bit slicing, where you can use the bracket operator and use it to extract ranges of bits from a larger signal, like a field, a bit field, right? Like, so you're going to be using this for your CPU to take like the opcode out of an instruction, for instance, or registers or function codes out of an instruction. We also talked about bit combining, where you use the curly brace and you can concatenate bits together to create a larger signal. And then there's this duplication, which is really strange, but you have to use 2 sets of curly braces for this. And you can duplicate, like in this case, I'm going to create 4 duplicates of bit 1 inside of A. And then there's also this thing called reduction operators, which I don't think we ever use in this class, but I think it's pretty cool, where you can take all the bits of A and feed them all into an AND gate to produce a single output, right? So this essentially creates 1 bit from many, essentially. That's why they call it a reduction operator. And it doesn't, I don't personally tend to see that used too often, but I think it's kind of neat. Okay, so the next topic is how do we create more complex behavioral HDL? And so to do that, it relies on a thing called a process, or in Verilog, they're called always statements, and in VHDL, they're called, I already forgot. I forgot the name. I'm getting old, too old for this. Process. It's just process. Yeah, they're called processes in VHDL. But the idea is the same, where this allows you to create what is effectively like an assign statement, a logic circuit, but you can use more complex language constructs in it, like if statements, loops, and case statements. Also, one thing you can do with an always that you can't do with an assign is you can infer memory with a, this is how you create flip-flops and RAMs, or with an always, okay? So the problem with always, it gets a little complicated because there's different variants of the always statement. So basically the idea is that you say always, and then you give it what's called a sensitivity list, just a list of signals that when any of those signals changes, it activates the always statement, right? So it creates like it's like a list of a list of signals whose change in their state causes the always to run, basically. But if you are creating an always statement to make combinational logic that doesn't have any memory, right, then no one actually wants to write the whole sensitivity list out, because it would basically be all the inputs to the combinational logic, right? So instead, what they do is they'll say always at star, right? Which basically means I'm creating combinational logic. Anytime anything inside this always statement that's used as an input changes, I want to activate it automatically. And in SystemVerilog, they introduced this new one called always underscore comb. Okay, so that's the one I hope you guys use, although the always at star is so common in Verilog code. Often students in this class will use that form. Right? So basically, always underscore comb or always at star are 2 different ways that you create combinational logic, meaning that there's no memory. Anytime any of the inputs change, the output updates immediately, which is exactly how the continuous assignment statement works. The only difference is that, well, actually, the only difference is that the continuous assignment is just like one statement, whereas an always block can be a little bit more complex, and I'll explain that more in just in a second. Now, there's also the ability to create sequential logic or logic that has memory in an always block. And for that, you typically will have always at, and then you'll put a clock signal, meaning that you don't want the always to activate. You don't want it to update anything until you get a clock, right? A clock edge or a clock level, right? If it's a latch. Typically, we use clock edges because we use flip-flops, right? And synchronous, edge-triggered RAMs. Okay? But there's another form of that, too, where you can say always underscore FF and then give it the sensitivity list. Now, what's the difference? The always FF and the always COM were introduced in SystemVerilog it was a way to double check the designer. So the problem is that when you're designing, when you're writing an always statement, it's easy to accidentally infer memory when you didn't need to. And so if you put always underscore com, you're telling the compiler that this is combinational logic. Or if you say always underscore ff, you're saying this is a flip-flop, not a latch. So it allows the compiler to double check what you've got in there. It's a little bit more safe. Okay, so let's look at some examples here. So here's an example of combinational logic. So I can say always underscore com, okay? Now, you can put one statement in an always, or you can put a block of statements if you put a begin and an end in there. Okay, so begin and end is just like, the curly braces. Okay, now notice here I have an if statement. So the only place you can use an if statement is in an always. You can't put an if statement outside of an always. Well, technically there's a preprocessor if statement. It's like backtick if. It's kind of like pound if in C, but that's for preprocessor. The only place you can put an if statement for the language itself is in an always. So inside this always, I say if select, then set out1 to be foo, else set out1 to be bar. Now, one of the things you'll notice here is that, look, I've got two different possible assignments for out1. Isn't that double driving it? Well, no, because for one, these are mutually exclusive because of this condition. But also, you can reassign signals inside of a always block. That's okay, because the only one that counts is the one that happens last after it's activated. So that part this is where things get confusing, because basically what I'm saying is that inside of an always block, it uses sequential semantics. But when the always block gets converted to hardware, the whole thing just becomes a circuit, right? Which really has concurrent semantics. Anything in its sensitivity list changes and it updates the output immediately. You see where I'm going with it? But internally, you can have sequential semantics, meaning that you can do things like ifs, the constructs that have a program flow to them, like an if statement or a case statement or even a loop, although we don't do loops in this class. But you can do for loops in here too. Okay? Sorry? Sorry?
You can do for loops?
Yes, you can. Yeah, you can do for loops in an always. Yeah.
So how do you write it? Just for something?
It's similar. The syntax is pretty much the same as C, except you can't declare the I inside the for loop. And there's no plus plus. You have to say I equals I plus 1. But it's similar to C. And then, of course, use begin and end for the body of the for loop instead of braces.
So if it gets forward, does everyone keep using them? It seems like you're solving a lot of problems with very long things.
Yeah, but the problem is the for loop is going to get completely unrolled when you synthesize it. So it's not a real for loop. It's not actually running with a program counter going through the loop. It's actually going to take the for loop and essentially completely unroll it and then generate a circuit that gives you an equivalent output from that for loop. Right? Yeah. So that's why we don't tend to use them in this. We use them. The only time we use them in this class, some people use them in Testbenches, which is non-synthesized, not code that doesn't get converted to hardware. It's just for testing, right? So if it's in a Testbench, it's okay. But generally, you don't put loops in hardware unless you're using a generate loop. That's a common way to do it. Like if you have some structure you want to repeat, like RAM or processor elements or something like that. Like if you want to create an array of multipliers, you can use a generate loop, which kind of stamps out a bunch of copies. But again, what that's really doing is unrolling and then instancing all the logic in the loop body. So this always statement is equivalent to the assign statement that I have above. So the assign statement above uses the ternary operator. This ternary operator says assign out1, checks the condition of cell, and puts out foo or bar to out1. These two are the same. Those two generate the same hardware. Okay. Okay, so basically, if you have, what ends up happening is that the always statement can have more than one output, unlike an assign statement. Well, again, a assign statement can kind of have more than one output if you use the curly braces on the left-hand side that combines, right? But generally, with an assign statement, you just have one you have one left-hand side, I should say. Technically, that's what I should say. It has one left-hand side. I showed you guys that? I think I showed you. You can actually have an assign and use curly braces to have technically more than one thing that gets assigned, but it has one left-hand side. Whereas in an always statement, you can have multiple left-hand sides, right? You see I have a left-hand side here and I have a left-hand side here, right? You can have more than one output assigned or set, or you can change the state of more than one signal as a result of an always statement triggering, right? So what happens is that all of the outputs within an always statement are then owned by that always statement in the sense that they are driven by it. They're electrically connected to that output that'll always. So you can't have two always statements driving the same output, setting the same output, or you'll end up with a conflict, or it won't even compile, as you guys saw earlier. Sometimes it won't even compile in that case, right? Make sense? Make sense? Okay. So likewise, anything in there that's on the left, anything in the always statement that's on the right-hand side of an assignment or that's used in a condition is considered an input. So in this case, there is an implied sensitivity list containing bar, foo, and cell. Bar, foo, and cell are all treated as inputs. So if the state of any of those signals changes, it will cause the always to activate. And it will update all of its outputs, which in this case, the only output is out 1. It's the only thing that's treated like an output. So in other words, what I'm trying to say is that always statements are kind of complicated because anything that's treated like an input is an input, and thus part of the sensitivity list if you use always comb, right? Anything that's treated like an output is being electrically driven by the logic circuit that's generated from the always statement, right? So you have to be careful there that you don't have multiple always fighting, for the same output or in conflict, right? Or you can have an always and an assign that are both driving the same signal. Or you can have an always and a structural expression, right? Like you have a module that's instance whose output is connected to the same signal. Okay, so I think I saw in lab that a lot of you guys use the, oh sorry, that's not the example, this one. A lot of you guys in lab figured out that you can put a case statement inside of an always, which is fairly, well, I shouldn't say standard syntax, not really a standard syntax, but it's close to what you're familiar with from C and Java. So you just say, and again, case only works in always. So I have always com, case data. Data is the input. And then I have the cases. And basically, I set segments depending on what case I go in. And then there's a default case. Makes sense? Now, in the case of case statements, you'll notice there's no break in there like there is in C, because each case is a basic block. So if you can perform multiple actions inside a case, but you have to use a begin and end. But in this case, I don't have a begin and end because there's just one statement associated with each case. And again, you don't need the break in there, right? So the syntax is a little weird. So this is actually a 7-segment decoder, although it's not this. It wouldn't work in lab 2 because I think the order of the bits is flipped, and I think this is active high instead of active low. And it only goes up to 9. We want you to go 0 to F in the lab too, right? You should go through all 16 hex digits in there. But you can use the same structure if you'd like for your hex decoder. Okay, here's another example where I have an always com, and I have 5 outputs, Y1 through Y5. They're all assigned. So A and B is the input. Again, A and B changes, it activates this case, and it will update all 5 outputs. And again, you could use you can use assign statements for this. It's kind of hard to argue why you need to use an always for that as opposed to just assign statements, but it's kind of up to personal preference. Okay, here's another variation. There's a couple of variations on the case in this case, we have a case statement, case Z, where you can actually have don't cares in the cases. So in this case, that first case says 1 question mark, question mark, question mark means that it'll match A, any value of A from 1, 0, 0, 0 to 1, 1, 1, 1, right? 1, 0, 0, 0 to 1, 1, 1, 1, right? Because we got the don't cares. Okay. Okay, so now what about memory? I mentioned that you can make memory with a always, and this tends, at least in my experience, it's usually when you see an always, they're used for memory because, like I said, that other stuff I showed you, combinational logic, you could do with assign statements. You know, you don't need an always for combinational logic, but you do need an always if you want to make sequential logic. So sequential logic is whenever you can lock a value in. You can have a state associated with a circuit where you lock a value in, and it will stay fixed until some event happens that allows you to update the internal value, right? So in this case, I'm creating a flip-flop. So this says always underscore FF. And again, the underscore FF is optional. The underscore FF is a SystemVerilog safety net, basically. You could just say always here, too, and leave off the underscore FF. But the underscore FF allows the compiler to enforce this being a flip-flop type behavior. So in this case, I'm saying pause edge clock. So pause edge is I guess it's a modifier. It's a way to, it's being applied to the clock. So clock is a signal. Pause edge clock is a way to say I only want to activate on the rising edge. And of course, there's a neg edge clock too, that's the falling edge, right? If you just put clock without the pause edge, it'll activate on either edge and any change in state of clock. So it'll activate on the pause, rising and falling edge. In this class, we pretty much use pause edge for everything, just as a convention. We don't do any fancy like double data rate stuff where we're operating on both edges of the clock. So in this case, you have an output Q and an input D, and whenever you get a rising edge of the clock, Q is updated, it gets D. So this is basically like saying that it's like taking a snapshot. Whatever D is, you take a snapshot of it whenever you have a rising edge of the clock, and then that value gets retained. Now in this case, this is a very simple flip-flop. It doesn't have an enable or a reset. So basically all this thing does is it acts as a delay, a one-cycle delay. So whatever you see coming out of this flip-flop will always be what D was in the previous cycle. Okay? So that's useful for pipelining. Whenever you want to move, you want to have a value to move it into basically you're taking a value and moving it one cycle into the future, is the way I like to think of it, right? Because one cycle into the future, I will see the value as it was now, right? It's a delay of one cycle. Now you can add a bunch of other behaviors in there. You can say, in this case, we're adding a reset. So this says, if reset, then Q gets 0. Notice Q is 4 bits. I don't know if I didn't mention that in the last slide, but it was 4 there too. Yeah, Q and D are both 4 bits. So it's not a single bit flip-flop, it's a 4-bit flip-flop, which generally is just called a register, right? So on the rising edge of the clock, you can reset to 0 if reset is asserted, or otherwise you just lock in whatever the value of D was on the rising edge. Now the problem with this, though, is that this ends up being a synchronous reset because the reset won't work. The reset's ignored until you get the rising edge of the clock. So this is as a synchronous reset. So we just found out, I didn't realize this until the beginning of this semester, but I asked Alex to run a timing analysis on his CPU. So Alex took this class last fall, and he's a new grad student this semester. And so he's a TA this semester. But previously we just used we have a 50 megahertz clock on the FPGA board, and we just used that. We never really looked at the timing, like to see, well, can you run it faster? Like we never checked. So Alex ran a timing analysis on his CPU, and it turned out that he used this synchronous reset on all his registers on his CPU. And it turned out that was the thing limiting the clock speed, because as I didn't know this, but on the FPGAs that we're using in this class, they don't actually have a real synchronous reset in the primitive flip-flop circuits on the FPGA. They only have asynchronous. So because he used a synchronous, the compiler actually had to synthesize the behavior of the synchronous reset, and it had to take the reset signal and route it as a regular logic signal instead of on a global network on the FPGA, which could only attach to the asynchronous resets. And it turned into a bottleneck. Basically, it crippled his CPU. So with FPGAs, you really ought to, at least the FPGA that we have in this class, the Cyclone 4E, the other FPGAs might be different, but the ones that we use in this class, you should use an asynchronous reset, which means you need to add the reset to the sensitivity list. So you can put pause edge clock, comma, pause edge reset, and that will create an asynchronous reset that allows you to reset the value of Q even without a clock edge. As soon as the reset goes high, it resets it immediately, right? And so you get two different behaviors. And this maps to the physical hardware more efficiently, apparently, as we've just learned. You could also add an enable. So you can add an enable. Now the enable is not part of the sensitivity list because the enable basically allows you to lock a value in to the flip-flop even when you get a clock edge. So this would be useful for if you have a register in your CPU that you only want to update under certain circumstances. You don't want changing every cycle. So what would that be? Well, in our case, that's going to be the hex display. So we're going to have in your CPU in class, we're going to use a control register, a RISC-V control register to control the hex displays. Like right now, you've wired them directly to the switches. But in the next lab, we're going to give the CPU control over the hex displays, and it's going to come from a control register. We don't want to change that control register unless we're executing a control register update instruction, which is the CSRRW instruction in RISC-V, which means that you're going to need an enable for that. So you're going to have a register called hex out that will have an enable. That enable will get triggered when it's time to execute the CSRRW instruction. Okay, so you might have noticed in the code that, let me back up here. I didn't bring this up, but you might have noticed that in this always underscore comb, the equal signs are just equal signs, right? And when I talked about sequential logic, the equal signs are now less than equal sign, right? Why is that? So this is also kind of confusing. So bear with me here. So less than equal is a non-blocking assignment. What that means is that when you assign something with less than equal inside, and this only works in an always, but in an always, if you use less than equal, if you assign something with less than equal inside that assignment statement, and then you reference it later. Now remember, inside an assign statement, it uses sequential semantics, meaning that there's like an ordering to the code. But if you assign something, and then you subsequently use that something as an input, like say you assign A, and then you say if A, right? Or you assign A, and then you add something to A, right? There's a dependency there, right? Because you assign something, then you use it. If you use a non-blocking assignment statement, basically anything you assign will only be updated after the always completes, right? In other words, if you assign something in an always with a non-blocking, then any subsequent references to that variable will be the old value of the variable, not the new value that you just assigned, right? So in other words, the non-blocking is a deferred assignment statement. It defers the actual setting of an output to when everything's completed, right? On the other hand, an equal sign is called a blocking assignment, and that allows you to honor read after write dependencies inside of an always statement. Okay?
So in case of non-blocking, all the statements are read after you assign all the assigned statements?
Yes, exactly. Yeah. So you assign it, but every time you read it after you assign it, you still get the previous state. It doesn't update the state until you finish executing, until everything closes out. So the difference is for example, here's two different versions of a similar thing. So I've got always underscore FF at pause edge clock. In this first one, I assign D to N1. Okay, and then N1 goes to Q. Make sense? Okay? So I have a dependency here, right? Because I write to N1. And then I read from N1 in the very next line of code, right? In this other one, I do the same thing, but I use an equal. The difference is this ends up creating a shift register because N1 doesn't get updated until I'm done, right? Which means that this Q sees the old N1, right? So what it ends up synthesizing is basically two registers that are connected in series, right? Essentially, it takes one cycle to go from D to N1, and then in a second cycle, I'll go from N1 to Q, right? So it's like a stage, it's like a pipeline of two stages. It takes two cycles for whatever's coming in D to make its way through Q, right? However, if you were to type this version ends up collapsing these two registers into one, because D gets N1 and then Q essentially gets D. So in this case, what it's basically doing is just replacing N1 with D, essentially, right? So this is only one register, this is two registers, right? Now, as it turns out, this actually applies across always statements too. This is, I don't know if you guys remember, but last week I set up a little test bench. And I had an initial block. I'm going to talk more about this in a minute. But I had an initial block where I initialized a value and then I incremented it for a test bench. It turned out I used the wrong assignment statement. That's why it wasn't working. I should have used a blocking for that test bench. So, but anyway, in this class, we adopt the convention that whenever you have sequential logic, just use non-blocking. But when you use combinational logic, in and always, use blocking. That's typically what's done. It's not a rule, it's just a convention. So here I've got pause, in other words, if it's clocked, if you have pause edge clock, use the less than equal non-blocking. However, if you have always comb, like I had here, always comb, use the blocking, right? That's just the convention. Okay? I mean, the point of that is to try to stay out of trouble, right? Because you can get into trouble with the blocking and non-blocking. You end up getting behaviors you don't expect. Okay, so this slide says what I just said there. Okay, so finally I mentioned test benches. So this is the last part that you need for lab 2 is you need a test bench, right? So a test bench is a module that you don't intend to synthesize, you don't intend to convert to hardware, you just want to run it in the simulation environment only. In other words, you're basically writing SystemVerilog for testing that's just essentially software that runs in the simulator, but you're going to wrap it around a design under test, which is the design that you do intend to put in hardware, but you want to test it, right? Now there's two ways you can do testing in the simulator. You guys, I might have showed you briefly last week. You can use tickle commands to force, and it's literally a command called force. You can force signals in the simulator, and you can even write a script, a tickle script that will go through a sequence of forcing inputs. And why would you force inputs? For the test inputs, right? What's called stimulus. You want to generate a stimulus for the design you're testing, some inputs. And then you want to look at the corresponding outputs. The problem is if you use tickle, you can do that, but usually if you're doing that, you're doing a small scale simple test, and you're just going to visually inspect the waveform, right? Whereas if you want to write a self-checking test bench, which is code that not only sets the stimulus, but also validates the actual output, then you should use Verilog for that, right? Now, I think technically Tcl can do that too, but, well, I don't know how to check stuff in Tcl. I mean, I could figure it out, but it's just not considered to be a good practice. Usually, your test benches should be in Verilog. Okay, so in other words, there's a simple test bench that just sets the inputs. You can have a self-checking test bench that sets the inputs to your design under test and validates the outputs, right? Or you can have a self-checking test bench with test vectors, which basically what that does, the test vectors allow you to put the test cases in a separate text file, right? So it just makes the test bench reusable. You don't have to hard code the inputs and expected outputs inside the test bench. Okay, so here's an example. So I've got this thing called silly function. It has 3 inputs and 1 output, and you can see it's just an assign statement. It's just a little snippet of Boolean logic. So I can create a test bench that the first thing the test bench does, well, aside from declaring, so it declares A, B, C, and Y. Why does it declare those? Because there's no input. Test benches usually don't have any inputs or outputs. They're kind of self-contained, right? Notice there's no inputs and outputs on the test bench, but there is A, B, C, and Y, and declared internally. And then the silly function is instanced as a DUT, design under test, and then I connect A, B, C, and Y to it. And then I use this thing called an initial block, which an initial block is used for 2 purposes. You can use it in a synthesizable code to initialize memory. In fact, we're going to do that in this class. You will have an instruction memory in your CPU that we're going to treat as a ROM, and we're going to use a command in the initial block to initialize it with your program that you want to load into it. Okay? In a test bench, however, an initial block is used to basically just set up the test bench or to run the whole test bench. In this case, we're actually running the whole test bench in the initial block because you can see we're setting A, B, and C. This is the input. And then we put this number sign 10, hash 10, whatever that is, right? That's a delay statement. That delays for 10 simulation units. That alone, if you put that hash mark in your code, that will automatically disqualify your code from being synthesizable. Because that hashtag thing, hash mark, that is not synthesizable. That is telling it that you want to delay for 10 simulation time steps. It makes no sense for something that you put in hardware. But it does work, but it's valid SystemVerilog. It just makes it non-synthesizable. Now, you might say, what's the point of even delaying? Well, because you set the inputs and then you delay for 10 units, that allows the outputs to come up and be visible on your waveform. It allows the outputs to persist on your waveform for 10 units along the horizontal axis, right, the time axis. Now, it doesn't have to be 10. 10 is an arbitrary number because remember that there's no delays, there's no logic delay modeled in a behavioral simulator like QuestaSim. So as soon as you change A, B, and C, Y, which is the output, is going to change after epsilon time, after a non-zero but infinitely small amount of time. So you have to put some delay in there. You have to put some delay or the output won't ever update. But that delay can be 1 unit, 5 units, who cares, right? I use 10 here just because it's a round number, right? So it just gives 10 units for you to see the corresponding output. And then you have to read the output, which is manual labor, right? You don't want to do that. You want to have it automatically check that. So the way that you can perform self-testing or self-checking is by putting an if statement in there. After the delay, you can just put an if statement and check Y, right? So you can say, I'm going to set A, B, C. Oh, and by the way, if you don't want to change, hold on, let me back up here a second. Notice that I don't actually set A, B, and C on every line here. I set A, B, and C initially, but then I only change C. Why? Because I want to leave A and B what they were, right? I only want to change C. Yes?
So last program, when you were doing the kind of same thing, you just keep adding 1 to the binary.
Yeah, I did that in the last, that's another way to do it. That's essentially what I'm doing here, but it's just manually. Yeah, but that's a good point. Yeah, this is going through a counting sequence. So I'm setting A, B, and C, delaying for 10, and then I check to see if Y equals 1. Why 1? Because according to the Boolean logic, that's what it should be, right? The 1 is what I expect the output to be. And so if it's not that, then there's this little, there's this $ display, and this will actually print a message, okay? So in our script, you guys, I'm sure you guys have already seen this if you've been working on Lab 2. So we have a script called CSCE 611.sh. If you pass that script a test bench, what it does is it simulates in a headless mode without the GUI. It just runs, your test bench. The expectation there is that if there's any errors, your test bench should print the errors, in which case they'll come out on standard output, right? When I run test benches, I like to have the GUI there because I want to see the waveform, right? But when we wrote that script, we had this kind of headless command line based mode, right? Okay, anyway, so yeah, this just basically just checks the output. Okay, but the problem is this is kind of cumbersome because you have to bake in all the inputs and the expected outputs have to be baked into the code, right? So that's not very good. So instead, how do we generalize the test bench? Well, there's a lot of ways you can do it. It's kind of, everyone has their own style for test benches. This approach came from the textbook, and what the textbook says to do is actually to use a clock to run the test bench, which means that on the rising edge of the clock, it can assign the inputs and then wait to the falling edge of the clock to check the outputs. Now think about this for a second. Remember, silly function is a combinational logic. The silly function itself does not have a clock input. It doesn't care about the clock. Now, a lot of design under test do have a clock, though, so in which case you have to be aware of what the clock is doing and how it interacts with the design under test. In this case, they're just using the clock as a substitute for having that hash mark thing, that delay, right? They're just using it to run the test bench, right? Okay, and then the other thing is this test vectors file. So a test vectors file is just a text file with one test vector per line. The test vectors can be in hex or in binary. In this case, they're in binary. And the bits can be ordered in whatever order you want because that's determined by the test bench. So in this case, this is basically a truth table. Notice that on the left-hand side, I've got the inputs that go from 0, 0, 0 to 1, 1, 1. And then on the right-hand side is the expected output. So this is essentially a truth table. And then the underscore is ignored in here. So that's just there for lining up the columns, Okay, so in here, I start out and I declare clock and reset. And then I've got A, B, and C, which are the same. I had those before. But I also have Y expected and Y. So in this case, I have to separate the expected output versus the actual output. So whenever you have a test bench, you have to make sure there's two versions of every output because there's the one that you get and the one that you want, right? And then I've got this vector num and errors, which are counters. Now this is where things are a little weird because you would think that if I've got counters in here that I wouldn't have to worry about them being logic, right? They would just be like an integer, right? Because it's just a program. But in here, we're still using logic, even though these are just meant to be counters and not necessarily, wires in a synthesized circuit. And then here's where the syntax gets really crazy. Okay, so the test vectors are held in an array. But it's a two-dimensional array because the depth is the number of test vectors and the width is the size of each test vector, right? Now you guys know that in C and Java, when you declare a two-dimensional array, you can say like int A and then bracket number of rows, bracket number of columns, right? But in Verilog, basically, they do two things. Number one, they swap the rows and columns. So normally rows are first, columns are second, right? That's usually how it is in C. That's the convention in C, and even in linear algebra, that's the convention, right? But in Verilog, the first numbers you see here, the first range of numbers, 3 down to 0, that's the columns. That's the width of the test vectors. And the second number, which comes after the name, is the depth. So the depth is 10,001, essentially, because it's 10,000 down to 0. So number 1, rows and columns are swapped in order. And number 2, the width is put before the name and the depth is put after the name, which I really don't like that syntax, but that's what they've adopted. I think the idea is that logic 31 to 0 is kind of like, the type of the element that's in the array. And then you put the depth after that. This is also how you declare rams as well. But in this case, this is being used for test vectors. Okay, so then you instantiate the design under test here and hook it up. Notice that y is connected to y, but that's the actual y expected is what we want it to be. And then we have the clock that gets generated. So this is kind of like having this is a clock generator inside the Verilog. The way it's implemented is with an always, with no sensitivity list. So after I just got done explaining how always statements have, sensitivity lists, this one just says always, and it just runs. It runs in a loop, basically. That's what it does. Okay. Now, an always without a sensitivity list also disqualifies your code from being synthesized. This is non-synthesizable only to do this. But if you say always and then begin, and then you say clock is 1, delay for 5, clock is 0, delay for 5, then it will repeat. This will generate a clock with a period of 10 simulation units. Okay? Now again, this clock is really just here to run the test bench. This is just one possible way to code this. Okay, then there's an initial block, and here's something else that's new. You've got a $ readmemb, which reads the file I showed you earlier with the binary values in it. And so this just reads from the file example.tv and puts it into the test vectors. If you would put readmemh, it would assume that there are hex values in there, but readmemb is reading binary values. So this basically just initializes the test vectors. This is the same way we're going to load your code into your CPU, except we're going to use readmemh. And then you also initialize the vector num and the errors counters. And then you reset. So we set reset to 1, and then it delays for 27 time units, and reset goes to 0. So this basically just does a little pulse at the beginning. And then there's an always at pause edge clock, and it's deliberately set up as pause edge clock because it's going to take each test vector in turn, because vector num, remember, is a counter that gets initialized as 0, and it's going to assign it to A, B, C, and Y expected. And then there's another always statement. This is a case where we're going to use the negative edge of the clock. And in this case, it says, if you're resetting, don't do anything. If you're not resetting, then just check to see if y equals y doesn't equal y expected, in which case you print out an error and increment the error counter. Now notice here it says if y bang equals y expected. I mentioned this, I think, last class. The bang equals is a not equals that is used for test benches only. Because in a bang equals, it will say that z equals z and x equals x, even though you can't really make that comparison in real hardware. So if you're doing synthesizable code, you would say bang equals, not equals, right? Whereas if it's a test bench, it's bang equals. That way you can literally put x's and z's in your test vectors, right? And then they'll compare. And then this next screen is continuing the always that is activated on the negative edge. So this increments the vector number. Again, this is all if we're not resetting. And then it checks to see if, notice here, equals. There's 3 equal signs. If test vectors vector num equals x, then you can complete, that means we're done. Because you'll get an x if you read past the end of your test vectors, right? Because remember, we only put 8 test vectors in, yet we initialized 10,001 locations, right, for them. So this is a way to finish, and then $finish ends the simulation. Okay, now if you're in GUI mode and you do pound finish in the GUI, it'll actually bring a window up and say, do you want to quit? And if you say yes, then you're done. You lose your results. You don't get to see the results of your simulation. You have to say no. If, on the other hand, you use our script, you run CSCE 611.sh testbench, the pound finish is actually useful because that's what terminates the script, right? I think if you don't have a pound finish and you run testbench, I think it might run infinitely. Or maybe it has a timeout. I don't remember how he did that. But the pound finish is actually generally going to be used in the test bench to end the simulation. Okay, that's it. Any questions about that? Yes? Questions? Okay, so for lab 2, you want to write a test bench. You can write it in any style you want as long as it's a self-checking test bench. Okay? So it's going to set inputs in your 7-segment displays, and then it's going to check the corresponding 7-segment encoded outputs, right? So make sure you have something in there for that tests in simulation. And you don't have to use exactly this type of test bench, but you have to put some type of test bench in there. Okay, now we have a few minutes left. Let me, one thing I feel like I don't do enough usually in this class is do these demos. I want to show you, let me show you a quick example here of some sequential logic. So, okay, let's say I have this module foo. Let me put a clock in here. So let me show you, like if I say always begin, and then say clock equals 1, no, sorry, 0, and then pound 5, and then clock equals 1, pound 5, and then end. So that'll generate a clock. Now, notice I use blocking here. I think, yeah, blocking for this, right? Because this is not sequential logic or combinational logic. It's part of a test bench. So I've got blocking in here. And then I can say always at pause edge clock. And then let's do something. Let's create a linear feedback shift register. So the way this works is you have a value, and you can set it to be basically shifted, the shifted form of the value. So let's make this an 8-bit value. So I'm going to put 7, I'm going to say 7 down to 1. So I'm going to shift it to the right, meaning that bit 0 gets shifted off. But the thing I shift into the left-hand side is not going to be 0. It's going to be some function of the other bit. So I'll say val 5, and then XOR, say val 1, and then comma. So again, this is just basically just taking, on every clock edge, it's going to shift val 1 bit to the right. But then it's going to fill in the bit on the left with whatever the old bit 5 was and the old bit 1 was, right, and XOR them, right? So this is called it's a linear feedback shift register that's of the type, it's called a Fibonacci linear feedback shift register, and this will generate a pseudo-random sequence of numbers. I mean, assuming that you set it up correctly, you have the right taps. So the taps I'm using are 5 and 1. I don't actually know if these are good ones or not. But we'll find out. And then I have to declare, let's see, I have to declare, so logic clock and logic 7 down to 0, 7 down to 0 val, right? So is this a test bench? Is this synthesizable? It's kind of mixed because the linear feedback shift register is synthesizable. So basically those two lines, that always statement, that could be put into hardware. But then this always statement can't. So I'm kind of mixing test bench code in with synthesizable code. But really, this always statement probably should be outlined into its own module and made the design under test. But I'm just trying to do this kind of quick and dirty. Okay, so I'm going to save that. Oh, and finally, one other thing. We need to initialize. So if I put initial, I need to initialize val to be whatever the seed of the random number generator is. So I'll make it like, I don't know, 8 apostrophe D5, I guess, something like that, right? Okay, so I have an initial in there. Now, normally, if this was an ASIC, the initial statement wouldn't make any sense because you can't actually, the reason initial works for this register is because it's an FPGA. When you configure the FPGA and you program it, it actually initializes all the memory is in there, right? So that's why I can initialize this. But if this were an ASIC and val was a register, I would have to use a reset signal to reset it. You couldn't just have an initial block because registers come up randomly on an ASIC. When I say ASIC, I mean, you know, custom chip, right? Integrated circuit, right? Okay, so let me see how badly I screwed this up. Vlog, it's still called myfunc. Oh, cool, okay, we're good. All right, so I just compiled it, and then inside of, I gotta go to the library tab. So I'm gonna add these two guys to the wave and run this. Okay, so you can see that it's updating the clock. And we want to zoom in, zoom in. So you can see, if you can see here, so you can see, yeah, you see it's generating this pseudo-random sequence, 773B1D0E87, right? The other thing you can do is if you're in Tickle, instead of having a test bench drive the clock, you can do a right click and you can say clock. And then it brings up this dialog box, and if you hit OK, it issues a tickle command. It says force freeze clock 100 50 nanoseconds, repeat every 100. And that'll actually force it to create a clock sequence. The problem with doing that is that when you restart your simulation, you have to reissue that command every time you restart. Whereas if you, in the test bench, if you generate the clock in there, every time you run it, it'll generate the clock. Okay, anyway, yeah, so there we go. I'll do a couple more demos next week, but in the meantime, I think we have enough to get Lab 2 done. And then next week, we'll start on the architecture part. Okay, thank you.